This is going to be the first video for Calculus 2, which is going to be integration techniques, and then we'll do some series and some sequences at the end of the course. But anyways, I need to motivate the whole point of integral calculus, so we're going to do one video on area, and we're going to discuss exactly what integration is all about, without really talking about integration yet. So here's some really simple problems. Find the area between the lines x equals 3, y equals 2, and the xy axis. Okay, so when we have a graph here, we want x equal to 3, so we have a line here. We want y equal 2, which is right here. So we know that this height is going to be 2, and the length is going to be 3, and we're asked to find the area inside of this box, which we know very simply that A is going to equal 3 times 2, which is equal to 6. That's pretty easy. Now, we have another example here where we have the line x equals 3 again. So let's draw this line out here. I didn't even hit my point. And the line y is equal to 2x, which I'm going to draw a little bit more slanted to fit it in, but we'll say that this is y is equal to 2x. So we want to find this area right here, which again is fairly simple because we know that our height here is 6 and our length is going to be 3. And this appears to be a triangle, so we know the formula for area is 1/2 length times height, which is going to be 6 times 3 over 2, which will equal 9. So again, finding the area of objects we know is pretty simple. However, when I give a question, like find the area between x equals 3, which here is the line x equals 3, and y equals x squared, well, this is a little bit more difficult because we're finding the area underneath a parabola. And this is not necessarily the easiest thing to do because we don't have any formulas for it. We can estimate it and say, well, this is kind of a triangle. So we would have, well, we'd have x squared. So this height would be 9, and this length here would be 3. So we could say that, okay, well, it's roughly going to be 27 over 2, which would give us the answer, oh, it's 13.5. But we know that's probably not right. In fact, if it were a triangle, we'd see a straight line like that, and we know that we've overestimated our area because we have all this extra stuff in a triangle that isn't going to be included in a parabola. So we know it's going to be less than 13.5 at this point, but how much less? And what methods can we use to determine this? So a brilliant dude thought of a nice way to estimate these points. And given a function here, f, and a continuous function on a closed interval going from a to b, so from here to here, we can estimate the area by making a bunch of rectangles at specific intervals. So we take the right-hand point and we extend it over to where the next interval is. So here I've divided it up into a number of rectangles. Of course we're going to go over and under the points, but that's okay. That just means that our estimation is going to be a little bit off. But what we can do is we can say, okay, well, let's take the endpoints on the right, and then we'll do the endpoints on the left, and we'll see what we get. So we have a bunch of rectangles now, and what we do is we just take the area of each of these rectangles, and then we add them together to estimate the area underneath the curve. And what we can do is if we want a more accurate result, we just split these rectangles up into thinner rectangles, and then we get something that more closely approximates the curve. So we get an even better approximation of what's going on. We have a definition here. We say, okay, delta x is going to be the gap between 2 points, so delta x. We let our first point be x0, and we let our last point be xn, and then every point that we have a delta x between, we just label it as the next x. So this point here is x1, this point here is x2, this point 3 is x3, so on and so forth, and they're all separated by a delta x. So x0 is going to be a, x1 is going to be a plus delta x. So to get to this point x1, it is the first point plus delta x. To get to x2, we take the first point and then we add 2 times delta x. So to get to the final point, which is just b, we take a and then we add n times delta x, because the number n is how many intervals we're going through to get to the final thing. So what this means is that to approximate the area for each rectangle, so what I'm going to do is I'm going to take just a new curve here. So we'll let this happen. This will be, ooh, that's not very good. We'll do a little graph here. I'm going to pick one rectangle. So we're going to pick this point right here. This will be a rectangle. We're going to have x2, x1. So the distance between the two, which we've said before, is going to be delta x. And the height of the rectangle here is going to be f of x2. So to get the area for this rectangle, it's simply going to be f of x2, which is the height, times delta x. So that's how we get the area of one rectangle. So to get the area of all the total rectangles using the right-hand side, we take f of x1 times delta x plus f of x2 times delta x, and then we keep doing this all the way up to f of xn times delta x. So I've taken the area of the first rectangle with f of x1 times delta x, then I take the area of the second rectangle with f of x2 times delta x, so on and so forth. Now, of course, we can factor out the delta x, so what we really have is delta x times f of x1 plus f of x2 plus all the way up to f of xn. So these f of x's we can calculate pretty easily just by plugging the number into the function, but what is delta x? Well, that's going to vary depending on how many rectangles you choose to do. So we have this formula here, delta x is equal to b minus a divided by n, which means what we do is we take the total distance. So again, I'm going to rewrite this. Let's do another one right here. So we'll rewrite delta x is equal to b minus a divided by n. So we'll draw a nice graph here, and we have this great curve. This will be our a, this will be our b, and what this means is we take the total distance, which is b minus a, so this distance again is b minus a, and then we chop it up into n intervals. And that means that each interval is going to be the distance divided by the amount of intervals. So this is effectively the distance over intervals. And that's how we get the delta x formula. So hopefully this is intuitive at this point, and we have a nice little method. I should reiterate once more that this method we use here, we give the title, or rather the notation, capital R sub n, because we're using the right side of a rectangle to determine the height of it. If we used the left-hand side, then we would say it's L of n, where n is the amount of rectangles we're using. So, what we really want to do to determine the exact area is, instead of having a finite n, we want to take the limit as n goes to infinity. So, what this really means is we make the rectangles infinitely small. So essentially, they're just going to be a bunch of lines up to the point. And because if the rectangles are infinitely small, we won't be overestimating or underestimating, we'll be getting the exact area. So we take the limit as n goes to infinity of Rn. You can also do Ln if you wish. I'll give you the formula for that later. And we saw before that the formula for R of n is f of x1 plus f of x2 all the way up to f of xn times delta x. And to make things a little bit more convenient, we use the sigma notation. So we say this is the limit as n goes to infinity of sigma I equals 0 to n of f of xi times delta x. Now, of course, this notation here, all it really means is you start at I equals 0, so here we plug in I equals 0, and then you add the next term up, so now you have I equals 1, all the way up until you get to the top term, which is n. So it's the same thing, we've just shortened the notation a bit so we don't have to write out an incredible amount of n's if we choose a large number. So that was a lot of theory, but let's put it to use. Let's find the area under this parabola using right-hand endpoints where n is equal to 3 and then when n is equal to 6. We won't take the limit as n goes to infinity mathematically this time because I need to introduce another concept next video, but we're going to see how the approximation gets a little bit better. So let's start when n equals 3, and we'll draw in some triangles or some rectangles to demonstrate what's going on here. So at this point, we make a rectangle over to 2. We make another one over to 1 here, and now we do 1 all the way over to 0. So we have 3 rectangles here. And you can see with these rectangles that we're getting a lot of extra area here. So this is probably going to be an overestimate. And what will happen, and I'll draw this in a second, but when we increase the amount of rectangles we have, we actually lose a lot of area that we're overestimating. So let's use the formula here. With R3, because n is equal to 3, we're going to have delta x times f of x1 plus f of x2 plus f of x3. Now we'll plug some numbers into this. We know that delta x is going to equal b minus a over n. So our final point is 3, and we're going to subtract 0 because that's our beginning point, so the total distance we're going is 3, and we want 3 intervals, which just so happens to be 3 divided by 3, which is equal to 1. Okay. Now our f of x1 is going to be, well, we'll have f of 1 plus f of 2 plus f of 3, because these are the heights of the triangle. And how do we get the height? Well, we have our formula here, y is equal to x squared. So this will be the same thing as saying 1 squared plus 2 squared plus 3 squared, which is the same thing as 1 plus 4 plus 9, which is simply going to be 14. So we've approximated that the area here is 14 using 3 rectangles. Now, of course, this seems to be a little bit high, because even when we did a rough approximation with a triangle, we got 13.5. So clearly, we're way overestimating. In fact, we're overestimating even an overestimate just made up out of our heads using shapes that we know. So let's try r equals 6, and we'll do 6 triangles. In fact, or 6 rectangles. In fact, what I'll do is I'll draw it again, because I do think it's good to have a nice visual aid here. So this will be 3, 2, 1, and now we have to put 6 intervals. So we're going to have one at 2.5, one at 1.5, and one at 0.5. So our rectangles now are going to look perhaps a little bit nicer. So we don't have as much overestimation as before. In fact, the old rectangle would stretch this extra area, but now we're only overestimating this area right here instead of all this extra area in this invisible box that we were estimating before and including in our area. So the only thing about taking numbers like this, for instance with 6, is that it's going to be a little bit longer. So now we're going to have delta x times f of x1 plus f of x2 plus all the way to f of x6. So what is our delta x? Well, our delta x is going to be 3 minus 0. That doesn't change, but now we're doing 6 intervals. So this is going to be 1/2. So we're going to take 1/2 times, well, our first height is going to be at f of 0.5, which I'll rewrite as f of 1/2. And this will be plus f of 1, plus f of 3/2, plus f of 2, plus f of 5/2, plus f of 3. So we can see here, we have a lot of terms. So if we want to go to like f of 20, or 20 intervals, it's going to be a lot of manual calculations. Anyways, let's put some things in here. This will be 1/2 times, and the reason I'm using fractions here is because 1/2 squared is going to be 1/4. And when we take 1 squared, we're going to rewrite that as 4/4. So when we square that, or rather we'll rewrite it as 2/2 and then square it, so we'll get 4/4. 3/2 squared is going to be 9/4. 2 squared is going to be 16/4. 5/2 will be 25/4. And 3 squared, which is 6/2 squared, will be 36/4. For some reason I was writing equal signs. Alright, so at this point we can factor out a 1/4, so we're going to get 1/8 times 1 plus 4 plus 9 plus 16 plus 25 plus 36. So when we add this together and multiply, we'll get 91/8, which is approximately going to be, that is 11 with 3 left, so we're going to get 11.375. In fact, that's not even an approximation. That is equal to it. And we can see here that our estimation is getting a little bit better. We've reduced the amount from 14 all the way down to 11.375 just by increasing the number of rectangles. In fact, what you find is that as n goes to infinity, the area is equal to 9, which we'll show algebraically or with limits next video using something called the Riemann sums, which is kind of what this is, but there's a little bit of more of a technical definition. And I did promise a formula for the left-hand limits. So if you recall, Rn is equal to delta x times f of x1 all the way up to f of xn. Now, what the left-hand limit does is it still takes delta x, but instead you start at f of x0, which is the leftmost point, and you go all the way up to f of x of n minus 1, which is going to be For instance, in this case, it would be the 2. So if I draw contrasting triangles here over the ones I drew already, we have the first rectangle being at a height of 0, then we have another one here, and we have the last triangle here. So you can see that the area in our left-hand endpoints is much less than the curve. And, of course, this means that this point would be f of x of 0, this point here would be f of x of 1, and this point here would be f of x2, and these would be the heights instead. So you can see we go all the way up to f of x n minus 1. So that is the formula for the left endpoints. And it should be mentioned that if you take the limit as n goes to infinity of Rn, it should equal the limit as n goes to infinity of left-hand endpoints. And of course, this is just your area underneath the curve. And we'll see how to do that algebraically in the next video. But that was a quick introduction to area. This is motivating integration, where integration really is about finding area. And you'll see much more efficient ways to doing this at a later point. But of course we have to do the hard, rigorous stuff first, and then we'll see a nice conclusion called the fundamental theorem of calculus that took hundreds of years to discover, that now is so painfully obvious and taken for granted that we don't even know what they did without it. But anyways, if you have any questions about area or motivating things, then leave them in the comments below and I will get to you as soon as I can.